All right, ladies and gentlemen, boys and girls, people of all ages, it's time to do some gas law problems. We're dealing with the ideal gas law. If everybody remembers correctly, that is PV equals and RT, right? Our pressure, our volume, is equal to the number of moles, the gas constant, and our temperature. Alright, this is just abbreviations and conversions up here. We don't really need to focus on that too much. You guys should already know that. Cool, let's look at problem number 1. How many moles of gas are contained in 890 milliliters at 21 degrees Celsius and 750 millimeters of mercury pressure? Well, let's just write out our PV equals an RT. We got that. So let's just fill in the blanks, right? We have 750. Our volume is 890, so we'll just make that 0.890 because we're converting milliliters to liters. And I think it's actually up here. Yep, 1 liter equals 1,000 milliliters, so you just divide this number by 1,000. That's going to equal, we're looking for number of moles, so N. Our R is going to be, we are in, we're in millimeters of mercury, so we need to get our gas constant to be 62.4, right? Our gas constant R, we need to match it up. 62.4 millimeters of mercury, so 62.4. And then lastly, our temperature is 21 plus 273, which is equal to 294. That means our N is going to equal, let's just do some quick math. Let's see, 750 times 0.89 equals 667.5. We're going to divide that by, okay, so this number right here is how much this is worth. We're going to divide this number by these two numbers multiplied together. So divided by, in parentheses, 62.4 times 294, close the parentheses, and then press equal. 0.4 moles. 0.04, excuse me. Glad I caught that. 0.04 moles. All right, I'm going to quickly solve through all of these now. We're doing the same thing over and over again. All right. 1.09 grams of hydrogen gas is contained in a 2-liter container at 20 degrees Celsius. What is the pressure in this container? We need to convert this to moles. We're looking for our pressure and millimeters of mercury, and we know our volume and our temperature. So let's convert this to moles real quick. So 1.09 times 1, or over 1 times 1 over 2. 1.09 divided by 2, 0.545. So now we're just looking for the pressure, so I'm going to write it like this. P times V 2 equals, and then our N is equal to 0.545. Our R, we're looking at millimeters of mercury, 62.4, and then temperature 293. All right, we're going to multiply all these together and then divide by 2 to get our pressure. 0.545 times 62.4 times 293 equals, divided by 2. We have a total final pressure, excuse me, 4,982 millimeters of mercury. Let's calculate the volume. 3 moles of gas will occupy at 24 degrees Celsius, 7.6 atmospheres. All right, we don't really need to do much here. We just do 7.6 times our V is equal to 3 atmospheres, so 0.08 0.0821, right? Look, see? 0.0821. We're going to multiply this by 297 degrees Kelvin. Let's multiply all that together. 3 times 0.0821 times 297. We're going to divide by 7.6 divided by 7.6. We get 9.6 liters. What volume will 20 grams of argon occupy at STP? Let's change this 20 grams to moles. Let's look on our periodic tables. Argon, 40. So this is equal to 0.5 moles. All right, now let's just calculate our thing. All right, so but I'm going to call this atmosphere, but it works any other way you call it because it's STP, but atmosphere just gives us 1 since that's standard. So 1 times our V, let's see here, times our V is equal to N, which is 0.5. Our R for atmospheres is 0.0821, and the standard temperature is 0 degrees Celsius or 273 degrees Kelvin. Let's see what this gives us. Get a volume equal to 11.2 liters. Awesome. This should have worked for any sort of unit you picked. Like if you picked kPa, kilopascals, instead of ATM, you would have gotten this answer. If you picked millimeters of mercury, you would have gotten this answer. It doesn't matter which one you pick. It'll all work out because of our R, because of our gas constant. Because it's different for each one. So that's why it works the way it does. Number 5. How many moles of gas will be present in a gas trapped within a 100 milliliter vessel at 25 degrees Celsius at a pressure 2.5 atmospheres? So let's do this. Let's do 2.5. 100 milliliters, so that's 0.1 liters. That's equal to, we're looking for moles, so we're looking at N. This is atmosphere, so it's going to be 0.0821. Then our temperature, 25 degrees Celsius, 298. We're going to do 2.5 times 0.1, and then divide that by this number right here. Divided by, in parentheses, 0.0821 times 298. Close parentheses, hit enter. Number of moles we get, 0.01 moles. Last two. How many moles of a gas would be present in a gas trapped within a 37-liter vessel at 80 degrees Celsius at a pressure of 250 kilopascals? We're looking at the same exact problem, just with different units and different numbers. 250. Gonna multiply this by 37. That's gonna equal, looking for moles, so N. We're in kPa, so we haven't used this one yet. It'll be 8.314. And then lastly, 80 degrees Celsius is 353 degrees Kelvin. If you don't believe me, I'll show you right now. 273 plus 80. Boom. I was right. Let's find our N. 250 times 37 divided by, in parentheses, 8 0.314 times 353. Oh, crap. Redo that. 250 times 37 divided by 8.314 times 353, parentheses, equal 3.15 moles. Awesome. Last problem. If number of moles of a gas are doubled at the same temperature and pressure, will the volume increase or decrease? If the number of moles of a gas are doubled at the same temperature and pressure, will the volume increase or decrease? The volume will increase. And I'll show you why. Look at this. PV equals nRT. This question is saying, okay, the number of moles is doubled. The pressure and the temperature stay the same. So we have our first, we have our second, right? We have two different readings we're looking at. If the pressure and the temperature are the same, we can cancel that out. The R is going to be the same. So now we're looking at if V equals N both times. Well, it has to. So when you increase Rn, don't even worry about this. When you increase N by any amount, when you increase the number of moles, your volume also has to increase so that the equation is equalized. And that's all that this question is asking. So if the number of moles of a gas are doubled, i.e. meaning that the N is now twice as big, but the temperature and the pressure stay the same, the volume must increase as well. And the volume will increase by a factor of 2, by the same factor that the moles increased. What volume will 1.27 moles of helium gas occupy at STP? We can solve this really quick. I'm going to do 1 atmosphere just because it's easy. We're looking for a V. It's 1.27. It's going to be multiplied by 0.0821. And our temperature is 273. Our volume is going to equal this. 1.27 times 0.0821 times 273 equals 28.5 liters. All right, guys. And look, that even makes sense, right? Because any gas, 1 mole of any gas is 22.4 liters, right? 1 mole of any gas. So if we have 1.27 moles, then it makes sense for it to be 28.5 liters. It's pretty close to 22.4, but it's not exactly. It's a little bit taller, or a little bit bigger. Not taller, but bigger. All right, go back and rewatch anything you need to.